In today's lecture, we will see Maxwell's equations, like what is a modified form of Maxwell's equation by considering the Ampere's law, Faraday's law, Gauss law, and also we will see what is conduction current and displacement current, because all these things comes together. It's an overall together understanding required, collective understanding required for understanding this topic. So this is actually the portion number 3.5 and 3. A part of 3.4. They have given it differently, so the collective understanding will is enough. Okay, so this is actually the last topic in your in module 3, and so now let's see what is it all about. Let's see. So this is actually based on the derivations of Maxwell's equations. Okay, so last class we have seen about Faraday's law. So rate of change of magnetic flux will result in an induced EMF. The same Faraday's law which you might have learned while studying transformers and all in your DC machines, I think, because you have DC machines and transformers this semester, right? So you might have studied there. So let's consider a coil which has n number of turns and a flux phi of t is passing through that. So we can say that an EMF will be induced, that is equal to minus of d by dt of all the flux. So if there is n number of turns, means we can take it as n into phi. Negative sign because of Lenz's law. All these things you can learn in machines. So no need of going too much into that. We'll see the electromagnetic parts of these things. So EMF is equal to minus d by dt of n into phi. So minus n into d by dt. So if n is equal to 1, it should have been d phi by dt. Okay, now we are moving on to the EMT part, EMT analysis. So this much things you might have learned in electrical machines also, and maybe in your lower classes also. I think we are studying Faraday's law and Lenz's law. Physics, I think we are studying all these things. So, and we know that flux phi is equal to B dot ds. So we can write EMF, it can be written as integral E dot dl, which is equal to, that is the voltage is equal to integral E dot dl, V is equal to EDL. We have studied this equation earlier. So integral E dot dl is equal to minus of integral over S, dou phi by dou t will become dou by dt of B dot ds, because this is same as dou by dot t of phi. So phi we have replaced with, B dot ds. So integral E dot dl is equal to minus of S dou B by dou t into ds. And now we apply Stokes theorem. So Stokes theorem will make integral E dot dl is equal to integral S del cross E ds is equal to minus of S dou B by dou t into ds. So we have written Faraday's law, the EMF equation. Then in the electromagnetic theory, what was the equation that defined that we wrote? Then we substituted phi with B dot ds, and then we applied the Stokes theorem. And now let's see. So once we apply the Stokes theorem, we can write, comparing those equations, we can write del cross E is equal to minus dou B by dou t, right? Here the sub integration and ds will get cancelled, which makes del cross E is equal to minus dou B by dou t, and this is called Maxwell's first equation in point form. So I think the last one class before I have made you write, I have given you all the 4 equations. So now, so the same equations only, but I think that time it was not in order. I didn't mention which was the first equation or which was the second equation. So this actually sums up everything. So del cross E. So after studying this, we will move on to Maxwell equations in time varying. So actually now what we are seeing is, actually earlier which I have, the Maxwell's equations which I have given you was for static field, static electrostatics and magnetostatics. What is the Maxwell equation? That's what I gave you in the earlier class. Now what we are seeing is time varying field, because last class we studied time varying field. So now for a time varying electric and magnetic field, how the Maxwell equations will be behaving, that's what we are seeing. So towards the end I will sum up everything, so then it will be, you will understand everything. So this equation is del cross E minus dou B by dou t, and so this is obtained from Faraday's law, and this is the Maxwell equation in point form. So Maxwell's modified Maxwell's equation from Faraday's law means this much is required. So that's it. That's over. Now coming to the second session, that is from Ampere circuit's law. So from Faraday's law it's over. Now from Ampere's circuit law. So now when we take the Ampere circuit's law, so from Ampere circuit's law, we have already obtained an equation. That is, for a static field, we have obtained del cross H is equal to J. So I'm not going into the derivation, and also you know this equation, del cross H is equal to J. Now we take the divergence. Now we take the divergence, that makes it del dot del cross H is equal to del dot J. So you know that del dot del cross H, that is divergence of curl. Del dot del cross H, which is divergence of curl. So what is the value of del dot del cross H? And the divergence of curl of a vector and 0. This makes it 0. And del dot J is actually, and which implies, give us del dot J is equal to 0. And last class, I think you have studied last class. So del dot J is equal to dou by dot T of rho V. What is this equation called? This is called continuity equation. So from del dot J is equal to dou by dot T of rho V, that which is the continuity equation. We get the continuity equation, but we can say that we already, but del dot J is actually 0, which makes dou by dot T of rho V equal to 0. That means rho V. What is rho V? Rho V is the volume charge density. So dou by dot T of rho V equal to 0. What does that mean? So we can say that if dou by dot T of rho V is equal to 0, that is rho V is not changing. That is the volume charge density. Rho V is not changing. Rho V is not changing. That means it is for a static field. So yeah, you obtain, so rho V is not changing means it is for a static field. So this continuity equation which we have written now is valid only for a static field. So it will not work. It is not working for time varying field. It is not working for time varying field. So now our aim is to make it happen for a time varying field. For that, what we do is, earlier our equation was del cross H is equal to J, which we realize now that it is applicable only for static field, because dou by dot T of rho V is equal to 0. That is, dou by dot T of rho V equal to 0 means, what does that mean? Not changing with respect to time. That is not time varying. So del cross H is equal to J. That particular equation is valid only for rho V is equal to constant. That is volume charge density equal to constant. That means it is not time varying. So in order to bring the time varying concept into it, what we do is we add another constant to it, that is G. One extra term, it's not a constant, we cannot say, because we want to make it time varying, right? So then how can I say it's a constant? It's not a constant. One extra term we add. So one extra term we add, which makes it del cross H is equal to J plus G. Now we will do the same operations onto that. We'll take the divergence, then del dot del cross H is equal to del dot J plus del dot G. And del dot J, you already know, continuity equation, that is minus dou by dou T of rho V, plus you get it like del dot G. And we already know divergence of curl of a vector is equal to 0, which makes it del dot G is equal to minus dou by dou T of rho V. So Ampere circuit's law, for a time varying field, we got it like del dot J is equal to minus dou by dou T of rho V. And we also know that del dot D is equal to rho V. Del dot D is equal to rho V, you know that. Then we will substitute that here. For rho V, we substitute del dot D, which in place give us del dot G is equal to dou by dot T of del dot D, which makes G del we can cancel, which makes G is equal to dou D by dou T. So what does that mean? That particular term G is varying with time T. So our problem is solved. We got it for a time varying field. This satisfies the equation for both static and time varying field. So this particular equation, it is satisfied for both static and time varying field. So this makes our equation del cross H satisfied for both static and time varying field. So finally we can say del cross H is equal to J plus dou D by dou T. So this is the modified circuits law, modified Maxwell's equation by from Ampere circuits law. So you got the derivation also. Del cross H is equal to J plus dou D by dou T, and this is called Maxwell's second equation in point form. And then we say dou D by dou T, that particular term is called JD, that is the displacement current. So this is the displacement current JD, and now we can integrate the equation on both sides, because we need the Maxwell equation in integral form, right? So now we can integrate the equation on both sides. We can say integral over S del cross H dot ds is equal to integral over S J plus dou D by dou T. So J is the conduction current and dou D by dou T is the displacement current. Dot ds, J is the conduction current. So conduction current is a normal current we have, and what this, so if you are considering a capacitor connected in a circuit, then the current passing through, I'm just giving you one idea. So if you consider capacitor, this current I is passing through the circuit will be the conduction current, and displacement current will be in between the plates. In between the parallel plates, the current that we have, that will be the displacement. We will see it in bit more detail. So now we will go ahead with this. So this is the conduction current, and dou D by dou T is the displacement current. We had written that in the previous slide. So by applying Stokes theorem, so once we reach here, we have the liberty to apply Stokes theorem. Stokes theorem will give us actually the privilege to apply Stokes theorem. So integral H dot dl is equal to integral over S J dot ds plus integral over S dou D by dou T dot ds, which in turn makes it integral of L H dot dl. So we have studied integral J dot ds, that is current density over the surface, that is equal to current only, because J is equal to I by ds, so it is I only, plus integral over S dou D by dou T dot ds. So what we can summarize and write, we can say that magnetic field intensity around a closed path, magnetic field intensity around a closed path is equal to the sum of conduction current and the derivative of electrical displacement, That is dou d by dou t we are talking about. Derivative electrical displacement through any surface. So that is one example that I gave, parallel plate capacitor and the circuit. So through any surface bounded by the path. Bounded by the path. Okay, so we have seen derivations of Maxwell's of Faraday's law, which was very simple for time varying field. But when we applied Ampere circuit's law, we realized that L cross H is equal to J is valid only for a static field. So in order to make it valid for a time varying field, we brought in G and then we worked out what was G. We brought in G and then we gave a definition for G. So we realized that it is a displacement current and how it is varying and all things we have seen, and we have written a summary statement also. Okay, and now let me see if you have any doubts on this. Now we will see the Maxwell equation from Gauss law in electric field. So we already know this equation, Q is equal to integral d dot ds. So integral of the surface d dot ds, and we know that Q is equal to integral over V rho V dV, where rho V is the volume charge density. Then we can combine them and write integral over S d dot ds is equal to integral over V rho V dV, and this is the Maxwell's third equation. So what does that say? The total electrical displacement through a surface enclosing a volume. I'll write down the total electrical displacement. The total electrical displacement through a surface. So this is actually through a surface enclosing a volume is equal to total charge within the volume. That's what we have written as the equation. The total electrical displacement through a surface enclosing a volume is equal to the total charge within the volume. So we can apply divergence theorem on equation 1. So when we apply divergence theorem, we can see that integral over V del dot D dV is equal to integral over V rho V dV, and this is the Maxwell's third equation in point form. So this is the Maxwell's third equation in point form. So only that much is required. That is from Gauss law in electric field, and now the fourth one is Gauss law in magnetic field. Gauss law in magnetic field. So what does that say? It's very simple. From Maxwell's first equation, del cross E is equal to minus dou B by dou T. So we have realized that, we have studied this, we have derived it, everything we know. Now we take del dot del cross E on both the sides. So minus del dot dou B by dou T, which makes it minus dou by dou T of del dot B. So you know that del dot del cross E is equal to 0. So that's how we have been doing all these cases. So we get dou by dou T of del dot B is equal to 0, in place del dot B is equal to 0. So we can say that divergence of B, that is divergence of B is invariant of time. So what is B, what is H and all you should know. I'm not going to repeat every time. So divergence of B is invariant with time. That is, even if B is changed, del dot B is equal to 0. That is, even if B is changed, del dot B is equal to 0. So this is the Maxwell's fourth equation in point form, which makes it, we can write integral over B del dot B dV equal to 0. That is integral over S B dot ds is equal to 0. So all these things are realization of Gauss law in magnetic field. So this is the Maxwell's fourth equation in point form. So we have seen all the four cases, and I will just summarize all the four now and related that to static field. So now we have seen everything for a time varying field, and now I will summarize them and then we'll give you an idea how it will be for a static field also. So the heading is law from which it is derived, then point form or differential form, and then the integral form. And we can see that one by one we will see now integral form. So first one is Faraday's law. So when we go to the Faraday's law, we have seen that del cross E is equal to minus dou B by dou T, and integral E dot dl is equal to minus of integral dou B by dou T dot ds. And when it comes to Ampere's law, del cross H is equal to J plus dou D by dou T, and integral H dot dl is equal to I plus integral dou D by dou T. So we brought in conduction and displacement current and all. We have just derived now. Then Gauss law in electric field. What was the equation we got? Del dot D is equal to rho V, and integral D dot ds is equal to integral rho V into dV. And then what was the fourth one? Gauss law in magnetic field. That means del dot B equal to 0. So integral over S P dot ds is equal to 0. So this is what we have seen in this class for the first half an hour, what we have studied. So we have seen that. I will just summarize everything. We were on to derivations of Maxwell's equation. So Maxwell's equation for a static electric and magnetic field, that is electrostatics and magnetostatics, we have already seen, derived, understood, did the numericals and all. Now last class we studied about time varying electric and magnetic field, and for a time varying electric and magnetic field, how the Maxwell's equations behave. For the same, Faraday's law, Ampere's law, and Gauss law in both electric and magnetic field, we did the we studied that. So from Faraday's law, we got it like the process. So Faraday's law means it should be a time varying field only. Okay, either the field should be varying or the conductor should be very, you might have studied these things in transformer. So, and then from Ampere circuits law, also we did the derivation, we bring in one extra term, which was the displacement current. Example also I told you, case of a capacitor, this one, and then we summarized it, and then we went to Gauss law in electric field, so d dot ds, everything we did, and then the Gauss law in magnetic field, and this is the summary for all the 4 equations. Is it clear? So we have these 4 equations for a time varying field. So now I will show you how this varies for a static field, this same equation. Okay, so you just need to study for time varying, and other things it will come on its own. So for a static field, you know that B will be a constant as well as D will be a constant. So we have studied that. Then the equations which we have studied earlier, we can summarize it as the same equations. Del cross E is equal to 0, integral E dot dl is equal to 0, del cross H is equal to J plus dot E by dot E not required. Then same integral H dot dl is equal to I. Then del dot D is equal to rho V, and integral over S D dot ds integral rho V dV, and del dot B is equal to 0. So integral over S D dot ds is equal to 0. This is for a static field. Same thing we have studied. I already written, taught you all these things. Then if this was in free space. So free space in the pratyeka, free space means current will be 0, current density will be 0, volume charge density will be 0. That is free space. It is a charge free region. Maxwell's equation maybe free space. So del cross E is equal to dou B by dou T, B only, which makes it integral E dot dl is equal to minus of integral dou B by dou T into ds. Similarly, second equation will be del cross S. So this is for a free space, okay? Don't get confused. Integral H dot dl is equal to integral of dou D by dou T into ds. And third equation is del dot D equal to 0, which makes it integral D dot ds is equal to 0. And fourth equation will be, so del dot B. So for examination point of view, I think only static and time varying is what they are asking you, but that they can ask for free space. Question free space on the mention Jaydal, you should not a part like a 3 marks in like a free space in the Chodika. Free space on the syllabus. You should know how to modify the equation. So that's all about Maxwell's equations for time varying as well as static, electric and magnetic fields.